Thus far, we've largely focused our efforts on determining the optimal model parameter for the constant model when our loss function is squared loss. What we will now do is change our loss function to be absolute loss and now try and determine what the optimal model parameter is in this case. So if we are using absolute or L1 loss, our average loss is called mean absolute error. And so what our average loss or empirical risk looks like is this. It's 1 over n times the sum of the absolute values of yi minus theta. Let's again revisit our toy data set of 5 observations, 20, 21, 22, 29, and 33. The loss for our first observation is the absolute value of 20 minus theta. So whatever theta is, the loss for the first observation is the absolute value of the difference between 20 and theta. Our average loss or empirical risk then is 1/5 times, the absolute value of 20 minus theta plus the absolute value of 21 minus theta, and so on and so forth. We're really doing the same thing as we did before, but instead of our losses being yi minus theta squared, they're the absolute value of yi minus theta. Let's take a look at what both of these functions look like. So on the left, we have the plot of the absolute value of 20 minus theta. To be clear, in these plots that we are looking at, the x-axis is theta, and the y-axis is the loss for that particular choice of theta. So what this is saying is, if I choose my value of theta to be, 27.5, whatever this is will be the loss. And so you can see here on the left, loss is minimized when I set theta equal to 20, which makes sense because when theta is 20, the output of the absolute value of 20 minus theta is 0, which is as small as possible. The average loss looks like this weird shape over here. So you can see that the average loss in this case is nowhere near as smooth as it was when we were using squared loss as our loss function. When we were using squared loss, the average loss looked like a nice parabola, but here it's actually a sequence of piecewise linear functions. And it seems like the value of theta that minimizes average loss is somewhere around 22. So it's important to note that the value of theta that minimizes average loss when we use squared loss and the value of theta that minimizes average loss when we use absolute loss are not necessarily the same, and in general, they will be different, right? We saw before that for this data set, the value of theta that minimized mean squared error was 25, while the value of theta that minimizes mean absolute error for our data set is 22. I want to again point out the fact that the mean absolute error in this case is a sequence of piecewise linear functions where all of these kinks or bends appear at our observations. You can see that where these bends occur line up with where our observations are. This is 20, 21, 22, 29, and 33 on the x-axis. So we know that the value of theta that minimizes mean absolute error is different than the value that minimizes mean squared error. And so now it's time to once again resort to calculus and determine what that value is for any data set. So once again, let's switch to the iPad and try and use calculus to determine theta hat in this specific case. So our average loss looks like this thing, 1 over n times the sum of absolute values of yi minus theta. We know that the derivative of a sum is once again going to be the sum of a bunch of derivatives, so it might serve us well to go off to the side and determine what the derivative of yi minus theta's absolute value is with respect to theta. To first do this, we need to re-express what the absolute value of yi minus theta is in a form that is easy to take the derivative of. To do this, we will recognize that the absolute value of x is really a piecewise linear function on its own, right? If the input to the absolute value of x is non-negative, you just return the input back, right? The absolute value of 5 is equal to 5. If the input to the absolute value is negative, you take the negative of it before returning it. The reason I bring this up is because it implies that we can rewrite yi minus theta's absolute value as a piecewise linear function as well. The absolute value of yi minus theta is equal to yi minus theta itself if the input to the absolute value is non-negative. So if this thing is non-negative, it means that theta is less than or equal to yi. In this case, the thing we're passing into the absolute value is 0 or greater, and so we just return it. In the case where theta is greater than our yi, we need to take the negative of it before returning it. So we have theta minus yi. Now, what all of this implies is that the derivative with respect to theta of yi minus theta, which is absolute value, is again a piecewise linear function. And so the two cases are the same. The case where theta is less than or equal to yi, and the case where theta is greater than yi. And in the first case, the derivative of yi minus theta with respect to theta is just -1, and the derivative of theta minus yi with respect to theta is +1. Now, a minor caveat to this is that due to the shape of the absolute value curve, which looks something like this, the case where the argument is 0, so right here in the middle, the derivative is actually not defined. And so this case, we actually can't include the equality condition there. And so here, this case is only true when theta is strictly less than yi. When theta is equal to yi, this quantity is equal to 0, and the derivative is not defined. Now, fortunately, we can just ignore that point here, and it doesn't really change our derivation, but it's just something to bring up just so that we are technically thorough. And so now we know what the derivative of our loss for a single point is, and we can plug that in to the derivative of our average loss. And so taking the derivative of our average loss with respect to theta, once again, gives us 1 over n times the sum of these pieces. So it's the sum of the derivatives of the absolute value of yi minus theta. Now, this sum is just a bunch of ones and negative ones, right? Because the derivative of the absolute value of yi minus theta is either -1 or 1. The case where the derivative of the absolute value of yi minus theta is -1 is the case in which theta is less than yi. So every time that theta was less than yi, we are summing a -1. So I can write this as the sum of all of the times where theta is less than yi of -1. The case where we add a +1, I can just write this as a 1, is when theta is greater than yi. And so the derivative of my average loss with respect to theta is now this thing. It's 1 over n times the sum of a bunch of negative ones, where we add a -1 every time theta is less than yi, our observation, and we add a 1 every time theta is greater than yi, so greater than an observation. And so what we now need to do is set this thing equal to 0 and solve for the theta that, minimizes our average loss. And so let's do that. So my average loss is 1 over n times the sum for every time that theta is less than an observation yi of -1, plus the sum for every time that theta is greater than yi of a +1. And this thing we're setting equal to 0, and we want to find the theta that satisfies this equation. I can multiply both sides of this equation by n to get rid of the factor of 1 over n out front. And what I can actually do is add this sum to both sides so that I can have one sum on one side of the equal sign and one sum on the other side of the equal sign, right? And the reason I can do that is because I can technically factor out a factor of -1 out front and then add this quantity to both sides. And so by doing that, what I end up getting is that this sum of a 1 every time theta was less than yi is equal to the sum of a 1 every time theta was greater than a yi. And so now we need to stop and ask ourselves, what do these sums really mean? They seem a little cryptic, but what's actually going on? Well, so if we add a 1 every time theta was less than yi, the left-hand side is really just equal to the number of observations that were greater than our choice of theta. So this is the number of observations greater than theta. Because if we add a 1 every time, this condition holds true, the total sum of all of those ones will just be, the number of observations that were bigger than our choice of theta. Similarly, the right-hand side of the equal sign is the number of observations that are less than our choice of theta. And so what we want to do is find the theta that satisfies this equation. We want the theta that's such that the number of observations greater than theta is equal to the number of observations less than theta. And now if you think back to some of our earlier statistical definitions, the number that satisfies the property that there are an equal number of observations to its left and to its right is the median of a set of values. So what this is telling us is that theta hat in this case, and this case is where we're using the constant model and absolute loss as our loss function, is the median of our y's, the median of our observations. Now, let's switch back to the slides and take a look at what's going on here. Down here, I have the number line with our 5 observations from our toy data set, 20, 21, 22, 29, and 33. And you can see that the value that minimizes mean absolute error is 22, which is what we observed before, because it has the same number of observations to its left and to its right. There are 2 points to the left of 22, right? Those are 20 and 21. And there are 2 points to the right of 22. Those are 29 and 33. And so in this case, theta hat is 22 because it is the median of our observed data set. And so, this is consistent with what we saw before when we plotted mean absolute error across this toy data set. This graph was minimized when we set theta equal to 22. And this sort of proves that, using squared loss and using absolute loss will generally give you different optimal model parameters. So our choice of loss function will impact what the optimal model parameters will end up being. Now, one thing to note is that our toy data set only had 5 observations, and so there's only one median or middle value. It's the third value if you arrange the values in increasing order. But let's say we had an even number of observations. So let's say our toy data set was 20, 21, 22, 29, 33, and 35. And so we've added this 35 here. And so the graph of our mean absolute error is now shown to the right. And you can see that there's no longer just a single unique value of theta that minimizes average loss. Instead, any value in this sort of flat region down here has the same minimal value of mean absolute error. It turns out that this region corresponds to 22 to 29. So any choice of theta in that range will have the same average loss. And that's because any number between 22 and 29 has the same number of observations to its left and to its right. Now, by convention, if we have an even number of observations, we typically choose the median to be the mean of the middle two. In this case, that would be 25.5. But the point of me bringing this up is that when we use the constant model and mean absolute error, there isn't necessarily just one value of theta that minimizes average loss.